Welcome everyone to Statistics on this fine Monday afternoon. While maybe our Mondays aren't quite as cheerful as they were at the beginning of the semester, I'm feeling a little bit that way. Still Monday, it still is an opportunity for new choices and new things to happen in this week, right? Blank slate, well, maybe a large list of things to do, but right, we have a full week to get all of those things done. So we'll give it a shot this week for us in this course, and hopefully things go well for you this week. I'm a bit optimistic, tired, but optimistic. So let's take a look at the schedule so we can get a grasp of where we're at for the semester, what we've got coming up, and what we have to look forward to. So let's take a look here. And I believe that I did not post the lecture from last Friday, so I'm going to double check on that after class today. And I believe we also have not received an email reminding me to take a look at the homeworks, or maybe you did over the weekend. I haven't checked my email today. So there's some assignments that need to be updated for their due dates as well. Feel free to send me an email right now during class if you are not someone who's already done that, because I need to update the due dates for sections 7.1 and 7.2, which is what we discussed last week. All right. Okay, this of course is not what we want. We'll take a look at these tables here shortly, but for Math 205, yes, excellent. We are in week 10, folks. That means that there is, including this week, 6 weeks of class left. So we have 9 down, 6 to go. And keep in mind that week 14, of course, we have Thanksgiving. So there's no class on Friday, no class on Thursday either. But we don't meet on Thursday, so that's not important to us. And then following that, the last week of classes, everyone is welcome to stay home, which is really quite nice for us. That doesn't change how we're going to do anything in week 15. The goal, if we can stay on pace like we should be doing, the goal is for us to only meet on Monday and Wednesday to talk about questions regarding the statistical project. And then on Friday, I'll post the exam. So it'll be the same process, post it on Thursday morning, and it'll be due Friday afternoon. And then the goal is then to have a nice cumulative final exam and final exam week, which will have several days to work on as well. Excuse me. So this is what we have going, right? We just took an exam last week. Hopefully you took the exam. I haven't checked to see if anybody forgot to. But we have exam last week, and then now nothing until week 15 in terms of exams. I did briefly mention the statistical project on Friday, and we will talk more about that statistical project shortly. Not today, but sometime this week or next week, you should expect to see an assignment pop up related to that. And of course, I'll discuss it and mention it. So that's what we got going on this week. 7.3, 8.1, 8.2. That is the goal for this week. In fact, we're not even going to try to complete section 8.2. We're slowing down. We're trying to have a nice pace where we're not going crazy, right? Nice pace. A little bit of breathing time. Hopefully, we won't have too many long sections. Of course, that makes it not super helpful, but should be okay. All right, so a little bit slower pace. And this week or next week, there will be an assignment posted for the beginning part of the statistical project. And then we'll kind of give an example. We'll try to take a look at an example in week 12 or 13. So that way, while you're all trying to relax a little bit during week 14, you can, we'll begin to collect data in week 13, hopefully, and then week 14 and 15. Put that data together and write a nice report, have a nice conclusion for the project. But of course, we'll talk more about that later. So if you haven't heard what it is about already, this will make a little bit more sense when we talk about it again. All right. So that's what's coming up. This week, just some content. That's not so bad. So we talked about section 7.1 and 7.2 last week. We'd like to take a look at section 7.3 today, which shouldn't be too bad. A couple of problems where we have some calculations to do, but we'll get there pretty quick. And beginning of the section. All right. So the sampling distribution of the sample mean, we've talked about some aspects of this already. In section 7.2, we talked about the mean of the sample mean, and we took a look at the standard deviation of the sample mean. So in this section, we'd like to take it a step further and say, well, what does that distribution look like? We know what the mean and what the standard deviation are, but there's still a lot of variation in what those distributions could look like. For example, right, we can find a mean and standard deviation for a data set that has a distribution that looks like this. We can find a mean and a standard deviation for a data set that has a distribution that looks like that. But we want to know what the distribution looks like, right? What does this look like for the sample mean? And it turns out that it depends a little bit on the sample size and a little bit on what the distribution looked like for the original data set. So we, of course, already know the mean of the means is the population mean, and the standard deviation of the mean is the standard deviation of the population divided by the square root of the sample size. So we already know that. What we want to do is we want to investigate what it looks like for the samples themselves, what the distribution looks like. So if this is, let's say that IQs are normally distributed and with a mean of 100 and a standard deviation of 16. So we have 1, 2, 3 standard deviations marked out in each direction. So this is the population distribution. So let's say we went ahead and took a look at the distribution for samples of size 4. Well, the mean of this distribution, right, the mean of this data set would be the mean of the means would still be 100, but then the standard deviation would be the population standard deviation divided by the square root of the sample size. Of course, that's 16 divided by 2, which is 8. So that distribution, right, when we compare it to the original, it would be much skinnier because now 3 standard deviations is 1, 2, sorry, center 1, 2, 3. Right? It takes hits 3 in half the time because the standard deviation is half of what it was over here. So what about samples of size 16? Well, of course, we would then have a standard deviation of 16 divided by the square root of 16, which is 16 divided by 4, or simply 4. So still a mean of 8, right? The mean of the means is 8, and the standard deviation changes by square rooting by the, dividing by the square root of the sample size. So now, right, this is 1/4 of what that standard deviation was. So we've got 1, 2, 3 standard deviations. 1, 2, 3 standard deviations in either direction is much, much shorter. So in order for us to still have an area of 1 underneath our standard normal curve, these would have to be much higher, right? Squished together, but stretched taller. We'll want to keep these 3 images in mind, these 3 graphs, because we're going to draw a collection ourselves that are similar. All right. So the central limit theorem essentially says that when we have a large sample size, the variable mean, right, the variable mean is going to be approximately normally distributed. Simple as that. For a large sample size, sample means are approximately normally distributed. That's it. That's the end. That's the end of the comment. That's the central limit theorem. And what did we not talk about? Well, we did not talk about the distribution of the actual population. So I don't care what the distribution of the population is. Okay. If we get the larger the sample size, right? If we get an even larger sample size, then of course we're going to have a better approximation of the normal distribution. So what do we mean by that? Well, let's take a look at an example. So this is an example from the textbook. And this distribution, right, this we would say is skewed. Let's try that again. Skewed right. Because we added a few values over here to pull it off to the right. So this is skewed right. That's the population data. Okay. This is the distribution of the variable number of people. So this is household size for some population. And we want to consider taking samples of size 30 from this population and look at the distributions of this, or the distribution of that sample size, or that sample. So this is the distribution of the sample means. And this, of course, isn't perfect, but this dark line here is the normal curve with a mean of, well, what did they say, 2.5, and then now a standard deviation of whatever it's supposed to be, okay, based on the information from the original variable. So we see that it becomes approximately normal. Now this number here is important. Right, 30. Why did we choose 30? Well, because 30, right, if you're talking about the number of households for a population, right, how many households are there in the United States? Well, a heck of a lot more than 45, heck of a lot more than 60. There's thousands upon thousands upon thousands of households in the United States. So if we're taking samples of only 30, then we wouldn't necessarily expect that to be terribly big. So when we say relatively large, we're starting to say that 30, it looks like it could be large enough. And in fact, that's essentially the rule that we'll want to use is that sampling, having sample sizes of 30, at least 30, will get us something that is approximately normally distributed. Okay, of course, larger is better. But this is going to be approximately normal even at size 30, right? Samples of size 30. So this is kind of a generic description here. If we started off with something that was already bell-shaped, then it's going to continue that normal distribution. But as we increase the sample size, of course, it's also going to make it a bit skinnier and taller. In the case of a J-shaped curve, as soon as we start talking about the sample mean, it suddenly becomes simply a skewed right curve in this case. And then as we take larger samples, it still looks approximately normal. You can see that it's not perfect. It got kind of some weird shape going on here, but that's pretty close. And then for a uniform distribution, if we were to take the sample, it becomes something that's still symmetric, but right, that's a triangular shape there. And then if we were to look at size 10, it already looks a bit more bell-shaped, and size 30, bam, that's fantastic. All of these look about the same. So by the time we get to 30, it's approximately normally distributed. And you want to keep that in mind. 30 is sufficiently large for us to say it's approximately normally distributed. Okay, and that is for the distribution of the means. Okay, that's not for the data set itself. The distribution of the means is approximately normally distributed when we are using sample sizes of at least 30. So this is just a further discussion, right? We already know the mean of the means. It's the population mean. We already know the standard deviation of the means. It's the population mean divided by the square root of n. And then if we know that our variable was normally distributed to begin with, then the distribution of the means is going to be normally distributed. Right, so is x bar. If the variable was originally normally distributed, so is the distribution of the means. If the sample size is large enough, n larger than or equal to 30, then we have that the means are approximately normally distributed, and we don't care what the original distribution was. Awesome. So let's take a look at an example of this. We've already considered the example of running the New York City 10-kilometer, New York City 10K. So this is just more discussion on the same thing. So as reported by a magazine, the times of finishers in this run are normally distributed with a mean, right? That gives us a population mean of 61 minutes. And a standard deviation of 9 minutes. That is the population standard deviation. Oh, come on now. Let's try this again. Population mean and population standard deviation. Okay, but still in reference to the variable x. But what we want to do is we want to find the mean in terms of the sample and standard deviation of the sample. So find the sampling distribution of the sample mean for samples of size 4. We'll do that again for samples of size 9. We'll construct some bar graphs similar to what we looked at earlier, and then obtain the percentage of all samples of 4 finishers that have mean finishing times within 5 minutes. So this is going back to our discussion on normally distributed variables. Okay, so we'll take a look at each of these things. So for part A, we wanted to find the mean and standard deviation for samples of size 4. The first thing to note is, let me just type it in there so we can read it and it fits nicely. First thing to notice is that since x is normally distributed, x bar is also normally distributed. Okay, that's the first thing that we need to notice there. Of course, if we want to use appropriate notation, x bar here, since the variable x is normally distributed, right, the population has a normal distribution, then x bar is also normally distributed. Nothing to worry about. We don't care that the sample is of size 4. All right, then for n equal to 4, the mean of the means is equal to the mean of the population, which is just 61 minutes. And the standard deviation of the means is equal to the standard deviation of the population divided by the square root of the sample size. Both of these were discussed in the previous section, so this isn't new. This first comment is the only thing that was actually new. But here we have 9 minutes divided by the square root of 4, so that's 9 halves. And leaving it as 9 halves is perfectly fine. If you wanted to write that as a decimal, you could say 4.5. Excellent. So for part B, we'd like to do the same thing for samples of size. Let's see, what did it say? Size 9. Of course, the same statement should be made since X is normally distributed, X bar is also normally distributed. But that made no reference up to what size the sample was. So take this statement for A and B. So for n equal to 9, right, we can find the population, or we can find the mean of the variable X bar, which is the mean of the variable X, which is 61. That doesn't change at all. The standard deviation, when we're talking about samples of size 9, will change a little bit. So we still take the standard deviation of the variable divided by the square root of the sample size. And the sample sizes, of course, will change. So 9 divided by the square root of 9, which would just leave us with 9 divided by 3, or 3. So if we wanted to consider for part C, we want to construct graphs similar to those in figure 7.4. Bear with me and I'll flip back to the figure that we're talking about here. This is the figure that we're talking about. We want to give the distribution of the variable itself, distribution of the first sample, and distribution of the second sample, or of the sample means rather. All right. So we've got, let's see, make some relatively straight lines here. And I want them to be about the same in each case. Okay, those are about the same size. And I know that my mean is 61 in each case. And what I'd like to do is I'd like to mark out three standard deviations in each direction. So 1, 2, 3, 1, 2, 3. But I want to keep those same markings on all three of our graphs here. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, so that refers to three standard deviations. 61 minus 9 is going to put us at 52. 52 minus 9 is 43. 43 minus 9 is 34. So 34 in each case is the lower side. 61 plus 9 brings us to 70. 70 plus 9 is 79. 79 plus 9 is 88. So 88 on the high end each time. All right. So for our three pictures here, we want to have standard deviation of 9. We want to have most of the data within 3 standard deviations. So the graph should be really close to the horizontal axis by -3 and +3 standard deviations. For the next one, we have a standard deviation of 4.5, half of what it was before. So somewhere around halfway is where we would actually want it to be close to the horizontal axis, which means it's got to be quite a bit taller. And then for samples, right, this is for X, this is for n equal to 4, and this is for n equal to 9. In this case, this standard deviation is 3, so it's going to be about 1/3 of the disbursement. So it should be pretty close to the horizontal axis there and there, which means we've got to be quite a bit taller in order to have that same area, right? The area underneath the standard normal curve in each case is 1. Or the normal curve, sorry, they're not the standard normal because they're not mean of 0, standard deviation of 1. They're just normal curves. Excellent, so that's A, B, and C. The last thing we wanted to do was obtain the percentage of all samples of 4 finishers that have mean finishing times within 5 minutes of the population mean finishing time of 61 minutes. So we're working with a normally distributed variable. So let's go ahead and try and figure out what we're talking about here. So if I have my horizontal axis, my mean of 61 minutes, and then when we were talking about samples of size 4, we had of course, still the mean of 61 and a standard deviation of 4.5. So if I go down 1, 2, 3, and up 1, 2, 3 standard deviations, 61 minus 4.5 would bring us down to, let's see here, that'd be 57, 56.5, minus 4.5 would be 52, and then subtract 4.5 would be 48, 47.5. That looks good. And then add 4.5 to be 65.5, add 4.5 to be 70, and then add 4.5 to be 74.5. So normal distribution should be pretty close at 3 standard deviations. So something like that. I was off a little bit there. That looks pretty good though. And then I want to find the percentage, right? Find the percentage of all samples that have a mean finishing time within 5 minutes. So I'm looking for the samples that have a finishing time within 5 minutes. So 61 minus 5 would bring us to 56. And 61 plus 5 would bring us to 66. And what we're interested in is we're looking for the percentage of samples that gave us a mean in this range. So we're just looking for the area under this curve. But in order to do that, we would use the normal distribution and use the areas underneath the normal, standard normal distribution. So standardize these. Of course, 56 minus 61 would be -5, so Z1 is -5 over the standard deviation, which is not 9, right? Our standard deviation here is 4.5. And then Z2 is +5, right? 5 above, divided by standard deviation. And I did not calculate these ahead of time, so I'm going to go ahead and punch these into my calculator. So let's clear that. I have -5 divided by 4.5, and that gives me a -1.111111. All right, that's pretty easy, -1.1111. Now, because we're working with a table that only gives 2 decimal places, observing the third is sufficient to know what the second needs to round to. And then, of course, positive 5 divided by 4.5 would just be the positive version. So this is 1.111. So all I have to do is look at the area to the left of this z-score, subtract the area to the left of this z-score, and I'll have my the red shaded region, the area desired. So just to help us understand what we're looking at here, I can find the area to the left of this z-score, and I can find the area to the left of this z-score, right? That gives me the area in common here. So when I subtract those two, I'm left with just the area of interest. So the area is equal to, all right, this is where we got to go to that table that we had up earlier. So I need the larger one minus the smaller, so 1.11. So I know that the second column is going to be having a 1 in the hundredths place. So I'm looking at the second column, 1.1, and then this guy, so 0.8665. Again, 1.11 gives me 0.8665. That looks good compared to my notes. And then I'm going to look for the area to the left of negative 1.1. So I return to my table, negative 1.1, negative 1.10, negative 1.11. So 0.1335. 0.1335. And this area is going to give us 0.7330. And then what we would like to do with that is we would like to interpret that. So I'm going to give myself a little bit of additional room here a moment. So I can type in comment. So we want to interpret it again in terms of sampling error. That is what the problem asked for. So what we would say to that is there is about a 73.3%, right? 73.3% chance that the sampling error made in estimating the population mean but in this case, let's put it again in the context of the problem, in estimating the mean finishing time of all finishers. So there's a 73.3% chance that the sampling error is, sorry, I'm trying to put all this together. It's a big sentence. There is a 73.3% chance that the sampling error made in estimating the mean finishing time, right? We're estimating the mean finishing time. What are we using to do it? Well, we're using samples of size 4. So estimating that by that of a sample of size 4. So if we take a sample of size 4, there's a 73 0.3% chance that that sample is going to be one of the ones that's in here. That's what we said. And what is in here? Will be at most 5 minutes. So this sentence might not be exactly how I may have desired to say it myself, but I wanted it to reflect that of the textbook and that which will appear in your homework. So I think that it asks you to just fill in the blanks for the homework or select the correct choice. And this is the wording that I believe that they are using. So that's why I chose this. So again, there's about a 73.3% chance that the error is going to be at most 5 minutes. Let's add a little bit more detail to that. There is about a 73.3% chance that the sampling error made by using a sample of size 4 will be at most 5 minutes. Okay, but what are we estimating here? Well, we're estimating finishing time. So there's a 73.3% chance that the sampling error made in estimating the mean finishing time of all finishers by that of a sample of size 4 will be at most 5 minutes. All right, so there's a lot of information there. Let's take a look at one more example. Of course, we looked at the situation where we have a normally distributed variable. So let's take a look at where we don't know. So a collection of researchers studied mortgage loans in an article. According to this article, the loan amounts of loans originated by a large insurance company lender have a mean of 6.74 million with a standard deviation of 15.37 million. The variable loan amount is known to have a right-skewed distribution. Well, of course, that should make sense for us that it has a right-skewed distribution. If we take a look at this being our horizontal axis, that of the loan amounts. If I looked at the mean of 6.74 million, and then I looked at 1, 2, 3 standard deviations to the left, and 1, 2, 3 standard deviations to the right, you should notice that immediately, right, as soon as I subtract 15.37, I'm already at, what would that be, negative 9 million. Right, to subtract another 15, I'm at a negative 24 million, subtract another 15, I'm at a negative 39 million. Of course, they're not loaning out negative $39 million, right? 0 is right here. They're not going to loan out $0. So what we've got is we have, let's see here, huge distribution like this, and then it just kind of fizzles out like that. So this, right, is right skewed. Of course, we're not going to loan out less than $0. They're probably not even going to do $10. You can find that in your back pocket of some jeans you washed a year ago. Okay, so loan amounts clearly skewed right. That should make sense for us. So we want to use units of millions of dollars. That is, we can use 6.74 and 15.37 instead of adding all the zeros in. We want to determine the sampling distribution of the sample mean for samples of size 200. So we've got, let's see here, the mean of the means is going to be the mean of the variable itself, which they said was 6.74. And then the standard deviation of the means is equal to the standard deviation of the original variable divided by the square root of the sample size. Standard deviation was 15.37 divided by the square root of 200. Well, another one that I didn't calculate ahead of time. So let's go ahead and punch that into our calculator. 15.37 divided by the square root of 200. That gives us 1.0868. Again, I like to use 4 decimal places myself. If you use 2 or 3, that'd be okay, but make sure that when you're submitting your homework that you are matching whatever they're asking for. So when we look at a sample size of 200, we have a mean, right? The mean of those means will be 6.74 million, matches the original mean, and then a standard deviation of $1.08 million, or 1.09 if we round it. So we should also, again, interpret within the context of the problem as it asks us to do. So the main thing, right, we already knew how to find the mean and the standard deviation of the sample means. What's new here is, what does the distribution look like? Well, is 200 larger than 30? Yeah, definitely is. So again, all it requires is for us to have 30 for us to have an approximately normal distribution. So the means are approximately normally distributed with a mean of 6.74 million and a standard deviation of, let's see here, we found that to be 1.0868 million. All right, so to put that in the context of the problem, for our samples of 200 loans, the sample mean loan amount, or loan amounts, are approximately normally distributed. Right, that puts it into the context of the problem. The first sentence that I wrote, the means are approximately normally distributed with a mean and a population, or a standard deviation of whatever it was. That didn't tell us anything about the problem itself, so, or the context of the problem. So for samples of size 200 loans, the sample mean loan amounts are approximately normally distributed, and then of course still with mean, so what did we say, 6.74 million dollars, and a standard deviation of $1.0868 million. Excellent. So now we've put it into the context of the problem. So that's what I'm looking for there, is the main thing. All right. So why can we answer this part, right? Why can we say that they're approximately normally distributed, even though we know that the distribution of the loans is not normal itself? Well, we've already talked about this. We already mentioned it, and we can still answer this because the sample size is relatively large. Right, that is n is greater than or equal to 30. 200 is in fact greater than or equal to 30. All right, and that's all that we have for this section. So again, all that we've introduced in this section is the idea that the sample means are normally distributed and under what conditions we know that they are, or approximately. So when the sample size is greater than or equal to 30, then the central limit theorem tells us that we have approximately normal distribution for the sample means, regardless, right, of what the distribution is of the original variable. All right, and that's it for the section. A couple of additional exercises I would recommend that you take a look at when the time becomes appropriate. You may want to consider that doing that now, in fact, as you are working on the homework for this section. If you have any questions, feel free to stick around and ask. Otherwise, that's all I have for you guys today. So you guys can have a wonderful day, and I will see you on Wednesday.